looks like we've got it flashing that it's recording, so we're good there. Real quick, it's time for a test. We're in week 4, so week 4 will be next week. Week 3 we'll finish up this week. We're going to start sound today. So we're going to be working with sound and looking at sound and that aspect. So this is chapters 13 and 14, I think it is, in you guys' book. If you're going back to look at the chapters, because I've used so many different books, it's hard for me to remember exactly what the chapter number is. But from that perspective, I'm going to go ahead and switch over to the computer here. If we go in and look at WebAssign.
So this Friday?
No, it's not. Test's not going to be this Friday. Test will be Wednesday. Next Wednesday. So we're in this class. The sound homework is due on the 31st. Actually, I'm going to change that so that you guys have a little bit of time to work on it, because I'm probably not going to get to actual examples today. So if we put it, and we'll have it due Monday. We'll have it due Monday. Nope, that's right, Monday. Specific day of the week at 5:30 p.m. So the sound homework is going to be due Monday at 5:30, which gives you a chance to work on it over the weekend, gives you a chance to get the extra credit points, and gives you a chance to ask me questions on Monday if you run into any issues. And then the exam will be on Wednesday. So if we go back and look at when homework is due, I do want to go ahead and get you to get the pre-work for charges, and charges, go ahead and get it done. I've got it lined up because we'll start electrostatics next week. So we'll start electrostatics. We may even start a little bit on Friday, depending on how far we get today and that part of it. So the test will be over waves and sound. Those are the two things that will be covered on this exam. And the test will be Wednesday, February the 5th. So that'll keep us all on track and keep us going, and we should be in good shape. And I have all the homework and everything in the grade book. So everything's now in the grade book. I kind of caught up on that stuff yesterday. I did not grade the quizzes yet. I will be grading those probably today and tomorrow. And as a point of information for folks, I will not be on campus tomorrow. I have a couple of webinar things that I'm attending, and I've got to try and meet with Pioneer Tech tomorrow, so I'm going to not be on campus tomorrow. But if you need something, email me, because I'll definitely be around my computer. So that kind of gives you a clue as to what my schedule is like. And I'll be over in Enid on Friday, weather permitting, because we never know what happens with the weather these days. So that's where we're at. So questions on that, questions on what's due for homework, anything like that? Okie dokie. So in the week 2 folder that you guys have on Blackboard, you've got a really nice introduction to waves. You've also got a pretty good crash course on sound, which covers the Doppler effect. And I've got how the human ear works. We'll actually look at a couple of other those pieces. So that's all in week 2. And then in week 3, I have a lot of things related to sound. A lot of really cool videos and things that are related to sound. What timbre is really interesting, and vibration and frames. There's a tone generator if you want to play with tones and look at tone generator. There's also some stuff associated with frequency and pitch, and I've got some cool standing wave type things as well. Yeah, so there's a lot of fun videos to really bring what we're talking about to life. And we've talked about so far that waves transmit energy, and this really demonstrates it pretty drastically. We've got a guy that's hitting a tuning fork that's causing the other tuning fork to resonate, and it's causing the ball to move. So waves do transmit energy, and this is actually using sound waves. and he's using a resonance box, and so waves can transmit energy. So and that one's been going around Facebook here recently, so that kind of gives you the piece. The other thing is I went ahead and opened up way down here at the bottom of week 3. This is the PowerPoint that I'm about to use, because I got to draw a lot of pictures, and we all know my artistic ability is limited. So we got to draw a lot of pictures. So this time I do have a PowerPoint, and we're doing lots of pictures, and we'll start from there. So we're starting with sound. Sound is a wave, right? So it's a wave. It travels in time. It's going to travel out spherically. And we started talking about, we had 2 types of waves, right? This is where we were last Friday. 2 types of waves. We have a transverse wave, and that's the wave that's like a pulse in a string. It travels up and down, and we can get it to move back and forth. Now, sound wave is a longitudinal wave, which means it's going to compress, expand, compress, expand, compress, expand. So we started with how does that wave travel with time and position. And on Friday, we actually looked at, you guys are seeing the overhead. On Friday, we actually talked about that if I was in here and I looked at this particular spring, it's going to not move in terms of space, but it will move in terms of up and down. So we talked about how when we went from simple harmonic motion, we actually went into waves and looked at the waves associated with it. So longitudinal, compress, think of your slinky, okay? Think of your slinky, because your slinky can demonstrate both types of waves. They can demonstrate the longitudinal and the other. Now, one of the things that you might look at in terms of vocabulary, because we talk about things a lot in vocabulary, this part right here is also referred to as rarefication, meaning we're going to make it less dense in the situation. We're going to totally make it less dense. So we're going to make it rarefication, and we have those things that are out there. We did talk about this on Friday, that we looked at the velocity of the wave is related to the frequency times its wavelength. So if I go back here, wavelength is going to be from point to point for one complete cycle. The distance, if I'm looking at the x distance, the point to point for one complete cycle. Period is the time that it takes to complete one complete cycle. And frequency is the inverse of the period. So if I look at that, frequency is measured in 1/seconds. Wavelength is measured in meters. I've got a velocity in meters per second. So for all waves, velocity is going to equal frequency times lambda. Now, we have talked a little bit about on Friday that I have 2 different types of waves. I have mechanical waves and I have electromagnetic waves. And when we have an electromagnetic wave, we know what the speed is. For an electromagnetic wave, we know what the speed is, and that's the speed of light. So we can apply this to most waves. We talked about constructive and destructive interference. And I think at the very end of class on Friday, we actually drew the 2 rocks or 2 pebbles in the pond with my lovely artistic ability. Since I don't have it, we started, we want to look at it. So we get constructive and destructive interference. Waves can pass through each other. Constructive interference, ultimately we're going to call resonance when we get to standing waves, because if I get constructive interference, I'm going to get resonance in my standing waves. But my destructive interference, so I can add waves together. And so I can either cancel each other out or I can increase them. So when we talk about a tuning fork is going to generate a sound wave. And if I take the old strobe cameras to it, you can actually see the vibrations on the tuning fork. And when you look at those vibrations on the tuning fork, what's going to do is if I think of a tube of air, and I get the tuning fork to push the air together, I'm going to increase the density. I'm going to kind of group all those air molecules together, and I'm going to increase the density, and it's going to send out a pulse. And you can think of this as a series of collisions, right? Because we're going to have those air molecules collide with each other. They're going to transfer their energy to the next air molecule, and it's going to go on out. And as the tuning fork vibrates, I'm going to get regions of high density, and I'm going to get regions of low density. And that is going to disturb the air, and it's going to swing right, and we get areas of compression and areas of rarefication. So when we start thinking about sound, first thing is I'm going to transmit a wave. And did you guys see the latest science news? They have done a 3D scan of some Egyptian mummies in their throats and then do 3D printing of the esophagus area to be able to give a voice to a mummy.
No.
Yeah.
Wow.
Yeah, it came out in my science news yesterday.
Wow.
Yeah, that they're doing 3D printing of, doing some of these. And if you really want to talk about it, it's pretty cool. I think they're called Time. There's a group out of the UK and Sweden that will go into buildings and will do incredible 3D mapping of spaces. And they actually did do 3D mapping of the Church of Notre Dame. And so one of the things in the fixing of Notre Dame, or trying the rebuild of Notre Dame, they're trying to also recreate the sound of the space, because the space has its own sound characteristics. And so they're trying to, that's one of the things that when they're going in for the design, is to see if they can preserve the unique sound of that space. But again, they did the Roman Colosseum. They've done a lot of they've gone in with all kinds of laser telemetry to get really incredible space mapping. But sound, so if I'm looking at sound, my vocal cords are vibrating, and you can all tell they're pretty harsh right now. I sort of lost my voice I sort of lost my voice before I did 8 hours of lecturing on Saturday. And so my voice is not the best, but we get sound that's produced. It's going to create, just like the tuning fork, our vocal cords are doing the exact same the tuning fork is. It's producing these vibrations that go back and forth, and it goes out spherically. Okay, sound is going to go out spherically. And according to Huygens' principle, which we're going to see several different times, that any point on the wave, especially a spherical wave, can be the source of another wave. So if I even block that, like on a ripple tank, it will create another wave that'll allow it to go through a little hole in a ripple tank. So we can get that part, and so we're creating it, and we're having that wave transfer back and forth. So if I look at how that goes back, I can see we can cause those compressions to be the amplitude, the rarefications being the troughs. But remember, the amplitude of my wave is going from that midpoint. When I'm defining amplitude is like this. But the whole idea behind sound is I'm actually going to create a pressure wave. And we're going to talk about pressure and sound, because how a microphone works, or how a microphone works, or how I'm going to use a sound detector, I'm actually reading a pressure. I'm actually getting a pressure against that diaphragm. So that's where we're going to get. And you've got a link here that you can go in and click on the link. And this gives us a physics classroom. And we got a cool little GIF of how the tuning fork is going to change the density associated with the pulses. And it gives you, the physics classroom's got lots of good other things in there. And little more physics tutorials on what's a mechanical wave, a longitudinal wave, is a pressure wave, talking about pitch and frequency and timbre. So when we talk about sound, we're going to use some characteristics to think about sound, much like we think about light. Light has color. Sound has certain characteristics as well. So that's one of the things that we kind of look at. So when we talk sound, because sound's just a wave, and the reason we care about it is because we have this lovely wave detection device at the side of our head. It's called an ear. And it's really interesting. We actually have stereoscopic hearing just like we have stereoscopic vision. And it's really funny when you encounter something that doesn't have stereoscopic sound. I don't know if you know it. I have Dalmatians. So we're on Dalmatian number 3. We currently have 2 Dalmatians living with us, Dalmatian number 2 and Dalmatian number 3. But Dalmatians have a defect, have a genetic defect that a lot of Dalmatians are deaf. They don't hear. And it usually is associated in the same defect from a genetic point of view for all you medical types. From a genetic point of view, blue-eyed Dalmatians are more likely to be deaf, and liver-spotted ones are more likely to be deaf. So that's kind of, there's not all of them, but that they're more likely. And even the black and white spotted ones can have the deafness associated with it. It's just, just the frequency with which this particular genetic defect shows up. But I have the middle Dalmatian, Dalmatian number 2, Dart. Our first Dalmatian was named Nitrate d'Argent. We called him Nitrate. Dart's Nitrate d'Argent. Nitrate was silver nitrate. And the current Dalmatian is Agnew, A-G-N-O-O-O. So for those of you who remember that AG is silver and O3 is nitrate, it makes black spots, hence the names for our Dalmatians. But Dalmatian number 2 does not have very good stereoscopic hearing. He has a real hard time pinpointing where the sound comes from. So it's really kind of interesting. But audible waves for humans are mechanical waves that hit in a frequency between 20 and 20,000 hertz. That's our audible range. Now, it's not linear across the range, and there are biological differences, okay? There are biological differences as to which people are tuned into which frequencies. Females tend to be tuned into higher frequencies than males. Anybody know why?
Kids screaming.
Baby cry.
Baby
cry. Yep. So those are up there. Infrasonic means those are frequencies below audible ranges. And if you watch the nature shows, you know that elephants actually communicate in human infrasonic ranges. They actually communicate in frequencies below 20 hertz. Earthquakes also can be infrasonic. And earthquakes, you can actually hear them. In some cases, you can hear them before you feel them, depending on the frequency at which the earthquake is going. So you do get some very interesting things that are happening. Everybody heard about the 7.7 yesterday?
No.
Yeah, there was a 7.7 about midway between Cuba and Jamaica that caused evacuations in the high rises in Miami. Because they didn't have a really good feel for how the high rises were going to react. And with a 7.7, that's a pretty significant one. That's a biggie. The one that caused all the damage in Puerto Rico was in a 6, and it's a logarithmic scale. And that's one of the things that we're going to talk about in sound. Sound is a logarithmic scale. We use decibels, and they're logarithmic scales. And if you really want to kind of review how to manipulate logarithms, in the appendix of your book has a real quick review of logarithms. Because when you're adding decibels, and I think you guys have a homework problem that says we start out with a horn that's at this decibel level, and we bring in 4 horns at the same decibel level. What's the new decibel level? You're going to be manipulating logarithms in order to solve that problem. And Appendix A is a really good review of those logarithms. So earthquakes, you can hear them. And in fact, when I lived in Salt Lake, I heard earthquakes all the time. I never felt them. We actually had a room that would resonate. We lived on one of the slopes of the Wasatch Mountains. We had a basement, and one of our bedrooms in the basement, if there was an earthquake further north, kind of in the Yellowstone region, the sound would travel along the mountain range, and you could actually hear them in our basement.
Or earthquakes loud?
Well, loud is relative.
Yeah.
Loud is relative. If you're right there at the beginning, yeah, you can. The intensity can be fairly high.
When they were fracking, I could hear like a crack or a pop, like a sonic pop.
Mhm.
And they were saying, well, it's not because of fracking, but
You can hear sonic. You'll hear them.
How does infrasonic? I know, like, even though you can't hear it, like your body still processes it. So they're like, how does it affect you? Because I've heard that like it can cause weird things, like it can mess with you. Too much infrasound.
Well, because it's a transmittal of energy. Okay, it's a transmittal of energy. I actually happen to know a lady that could hear in the infrasonic, and she was a neighbor to the refinery. And we actually had one day it was driving her crazy. Literally, it was driving her crazy. And she went through the refinery in order to find the piece of equipment that was causing it. And we did find, and she could pinpoint the equipment. We put a decibel meter on the equipment, and sure enough, it was a very high intensity, low frequency sound. And we had to mitigate it, so we put up sound deadening stuff around that particular piece of equipment that really helped her out. But sound, I mean, you can use, we all know the quote methods of torture. Horrible songs over and over again, right? That's a sound one. How many have seen the James Bond one that does the high frequency one, where he pierces the eardrum using high frequency sound? And if you followed the news last summer, there was the accusation that the Cubans were doing some of this sonic stuff to the U.S. Embassy and was causing illnesses. Because think about your ear, and that's why I want to, we may not get an opportunity to show it, but I've got 2 different ear videos that looks at how our ear works. Our ears work by hitting the right frequencies and getting resonance in the ear. But our ear is also our central gyroscope for our bodies.
for our sleep patterns and
Gyroscopes keep us balanced.
balance.
Keep us balanced. Just like if you think about your front wheel of your bicycle, if I try to turn it around on a gyroscope, I really can't because my front wheel is trying to keep me straight, steady. So your ear has those things in it. And so if you're dealing with sound and you hit resonant frequencies, now think about ultrasounds. Ultrasounds are frequencies above the audible range. So we've got infrasonic and we got ultrasonic. But we use ultrasound to break up kidney stones. We use ultrasound to, like a bat, okay? Remember what a bat does. A bat's going to send out a ping, and it's going to hear the reflection of the sound to come back. And that's what we use for ultrasounds to image babies, image heart valves, image kidney function, image a lot of different things because different human tissue has different reflective properties, just like different paints have different color reflective properties. And so we're going to use that information to help us come back. This is why it always drives me crazy that those people that are trying to do radiology, including ultrasound techs, don't have to take physics 2. I don't get it. Because this is where the fun stuff is for that. This is totally where the fun stuff is. And if you get a really, really good ultrasound techs can distinguish between bruising and infection, can distinguish a lot of different types of things that are happening. They can also tell you, well, this is a tumor versus scar tissue with experience. So you've got a lot of interesting things that are happening with just looking at the different waves, which is why we focus on sound, because this is the cool stuff. So we talked about it. We didn't spend a whole lot of time on it, but we know if I have a string and I pull it tight, and that's going to affect the kind of wave that I can set up in my string. And we know this from experience, because even if we don't play piano, or we don't play guitar, or we don't play a stringed instrument like a violin, we know we can tune our violin by changing the tension in the string. And we know that if I have a string or a G string or a C string on my guitar or my violin, they also aren't the same. The density of the string isn't the same. If you look at a guitar, a 6-string guitar, you've got 3 strings that are generally nylon, that are very similar to fishing line, and then you've got 3 metal strings that are in there that will cause the different tones that we're going to hear. But if I'm dealing with sound's traveling in a medium, and that medium isn't a string. Although that's why the old coffee can, or the old string telephone, where you had a string between 2 cans and you could use that. That's why that would work, because I could transmit sound through that string. But when I'm dealing with sound, I'm usually going through air. I'm going through water. I'm going through steel. I'm going through a variety of different things. And in that case, we're looking at the compressibility of our medium. We're looking at how compressible is our medium. So it's an elastic property. So remember back right before we finished with Physics 1, we talked about the bulk modulus and we talked about the Young's modulus, the characteristics of the material. We got to worry about the characteristics of the material when we talk about sound. And just like in the string, I can predict the speed of sound that's going to happen in air or water or steel or something like that. So the speed of the stretched wave and tension, we can do the force, so it's mass per linear density, and we can look at it from that perspective. I think you guys have like one homework problem where you're using it. I'm showing that to you because the real takeaway is the medium's going to impact how sound travels. And if you think about that, whatever affects the elastic property of the medium, like temperature, is going to affect the speed of sound. Okay, for you all here, you've done the simple harmonic motion in Tonkawa. You've done the simple harmonic motion lab, right? That was the lab you guys did last week. Today, you're probably going to measure the speed of sound. You're going to measure the speed of sound in a tube. Do you guys over in Enid already measured the speed of sound? Yeah. So you guys have already measured the speed of sound. So the speed is, and how close did you guys get over in Enid?
Oh.
Not really? What did you guys measure for the speed of sound?
Was it like way below? I don't remember.
They don't remember? It was 300 and something, so what was it? Joshua's getting it out.
Yeah, I don't have a 300 on my paper, so.
You don't have a 300 on your paper? Then my guess is you measured the length of your tube wrong.
I don't know, Solomon measured it for us.
Ah, okay. That length
And we were
of,
behind.
okay, because when you guys are doing it today, over here,
Mhm.
pay attention to the length of the tube, because it's gonna be highly dependent on your tube. And it is not usually the outside of the tube. Okay? So that's usually where people get, but you're gonna get, usually when my groups have done the speed of sound, they've gotten it within 2 to 3%. So, I mean, you can really get it fairly accurately. And the other thing is whoever's got a good snap, finger snap, is the other critical part. Because you'll need to be able to do the finger snaps. So you guys will measure the speed of sound. Now, the speed of sound in dry, standard air is like 331 meters per second. That's not what you're gonna measure today. You're gonna measure today somewhere between 340 and 343, depending on the temperature of the lab.
Why is it different?
Because temperature affects the elastic property.
Is it colder that makes it faster?
No. The warmer it up, it goes up. I'll show you that here in a second. Show you that totally here in a second. And so, and you get other Young's modulus if we're dealing with different types of material. So it really deals with, there it is. Now, your lab will give you a slightly different formula, but it's the same thing, okay? The lab will give you a slightly different formula for the temperature. You do have to use the 273 K in order for it to work. But the speed of sound is impacted by temperature.
Positively or negative? You cannot-
It's gonna go up. So if I'm at room temperature, we're at 343. At 0 degrees, we're at 331.
So in the night, will you expect sound to travel faster than during the day? Because I know in the night, sound
Okay,
travel
now
faster.
that's different. There's a different thing. So I don't know if you guys over in Enid heard it, that at night we tend to hear sound, we think faster than we do during the day.
Is it because it's quieter?
Well, you have less opportunity to break up the waves. Think about sound on a windy day. If I try to yell on a windy day and it dissipates, the sound's gonna dissipate. There's too much churn in the air, it's gonna break up those waves. It's gonna break up. So what happens at night, we tend to lose the wind. We tend to lose the wind a lot.
Big.
Yeah, so we're not gonna get that dispersion of the sound. So that's because the daytime, remember, we have a lot of convection things that are happening from a temperature point of view. We have a lot of convection that's churning up. So that's one thing that happens. The other thing is you'll know, and if you think about it, if you're listening to sound, if I am downwind from somebody, I am likely to be able to hear them better than if I'm upwind from somebody, because I've got the air churning is breaking up those sound waves. So at night, one of the things that we notice at night, we don't have as much convection heating and convection activity, so we're likely to be able to hear it better. So that's one of the reasons that you hear things a lot better at night. Also think on a snowy day. What's happening on a snowy day? We have a lot of deadening, a lot of sources that are gonna deaden like a room that's gonna soak up.
Insulates it more.
We're breaking up the sound waves, we're getting more destructive interference, so we're gonna have real quiet. We'll have very, very quiet, because if you think about snow on a microscopic scale, you look at the surface of snow, it's very, very coarse. So we get things that break it up. Now, the other thing that this does not account for is relative humidity. All right? Relative humidity also can affect sound, because now you're not only just having sound transmit through air, you're having sound transmit through water. And so you do get some differences there. But and that's why we say in dry air, you know, this is the thing that will affect dry air. And that's also, depending on whether or not you had a lot of rain that day, that will impact your values as well. But dry air is one, so we get the absolute temperature. So when you guys do it today, you'll look at it from that perspective. So now, we get, and this is one of those things that P in this case is power, all right? P is power. Sound is a pressure wave, but we look at intensity related to power. And remember what power is. Power is work divided by time, right? So power is work divided by time, and we're looking at that change in energy. Work is a form of energy, and so we're looking at the power per unit area is what's going to be described as intensity. So when we're thinking about intensity of a sound wave, it's power per unit area, and it's measured in watts per square meter. So think about your eardrum. That's a little bitty place to be putting a whole lot of power on. That's why we end up with don't overstress your eardrums with your earphones cranked way up at high volume. Because ultimately what that's going to do, it's going to damage your hair cells inside your ear, and your hair cells don't regenerate. We aren't squids. There is an animal out there that can regenerate their hair cells. And they're doing lots of studies to try and figure out how they can do it. The other thing that happens to us as we get older, it's not just a function of our hair cells falling off. You've got a lot of calcium in your ears. You got a lot of calcium carbonate in your ears. And so there's lots of things that are going on. You actually have rocks in your ears. And so we've got some things that are going on in our ears as we age. We tend to calcify. That's what we do. So we have things that are happening that's going to cause the change in our hearing. Now, you can be you can lose specific frequencies due to traumatic impacts. But intensity is one of those things that we have to worry about. And so the rate of transfer of the power, we do it in power per watts per square meter, and that's where we deal with intensity. Now, hearing, okay, hearing is, let's see, I'll go in there just a second. So hearing, we look at in terms of decibels, because we don't typically measure intensity. And we're going to compare it with the threshold of hearing and our intensity. So the threshold in hearing is 1 times 10 to the minus 12 watts per square meter. That's our threshold of hearing. That's I sub 0. Threshold of pain is 1 watt per meter squared. Your ear is an incredibly sensitive device. It can hear over 12 orders of magnitude. 12 orders of magnitude. And we can detect pressure fluctuations in 3 parts of 10 to the 10th. So now you understand why decibels are done in logarithmic fashion. Because it really is a nice scale to look at our ears. It's an incredibly nice scale to look at our ears. Okay, so we don't have Adobe Flash. That's what I was afraid of. Allowance. Okay. So here's our ear structure.
There are 3 regions to the human ear. The outer ear gathers sounds and funnels them to the middle ear. The middle ear amplifies the sound waves and transmits them to the inner ear where the sound receptors are located. Pressure waves that are funneled through the auditory canal cause the thin membrane called the eardrum to vibrate. The 3 tiny bones of the middle ear pick up and amplify the vibrations. The stirrup pushes against the oval window of the fluid-filled cochlea. causing receptors in the cochlea to send signals out along the auditory nerve. Imagine that we could unwind the cochlea and watch what happens inside when there is a sound. Vibrations are transmitted from the eardrum to the tiny bones of the inner ear. The stirrup strikes the oval window, creating pressure waves in the cochlear fluid and vibrating the membranes between the cochlea's chambers. This vibration is the key to the perception of sound. In cross-section, you can see that the cochlea consists of 3 fluid-filled compartments. The sound receptors are located in a region called the organ of Corti. The organ of Corti sits atop one membrane and is covered by another membrane. When pressure waves move the lower membrane up and down, hair cells in the organ of Corti bend against the upper membrane. Action potentials arise, and messages travel along the auditory nerve to the brain. Now let's check what you have learned. Drag the text to the boxes to label the structures involved in hearing.
So you've got a pretty cool little animation that you can play with and get there. But think about that for a second. Remember when we talked about Pascal's principle, that if I have a fluid and I have a fluid that's contained in a vessel and I press down on that fluid, the pressure is going to change throughout the vessel. So the key to what's happening is as we get those changes in pressures, we've got certain hair cells that are going to react to it, which is going to give us our nerves. Now remember, those are the 3 smallest bones in your body, right? The anvil, the stirrup, and the little gizmo there. Those are the 3 smallest bones in your body. And that's how we end up with the sound. So we're going to use the thing that we call a decibel. It's a logarithmic function. It's a log 10. 10 times the log of the intensity divided by the threshold of hearing. Intensity is a physical quantity. Intensity is the conventional mathematics to a logarithmic scale. But intensity is our physical quantity. How we're going to be able to measure it and deal with it is by decibels. So we can look at those decibels. So, what are some of our typical sounds? A quiet room is usually around 40 decibels. Threshold of pain is 120 decibels. Things like jet engines, big compressors, lots of other things. Rock concerts tend to be between 110 and 120. It's why you can't hear the next day. And I don't know why people want to stand right in front of the speakers. Because you're going to feel them. We all know you can feel them because somebody's usually sharing their music with you with their subwoofers in their car. You know, we get, they're so nice, they're sharing. So, which means if you're sharing it loud enough for us to hear it outside your car,
You gotta be doing damage.
I'm thinking we got a problem inside the car. All right, we got a problem inside the car. We've got normal piano practice, soft radio music, symphony halls. You can go out there and you can find all kinds of different tables that are going to show you different thresholds of different things for different sounds. Now, let's talk about the Occupational Safety and Health Administration. There is an 8-hour time-weighted average that says it's safe for your ears. So if you're working in a work environment, OSHA says that you do not have to wear hearing protection if that work environment has a normal decibel level of less than 90 decibels. You have an action level at 85. Remember, we're dealing with a logarithmic scale here. So 85 to 90 is a big change, but we have an action level of 85. That's when we're going to tell people they need to be wearing hearing protection because we don't want them in an environment that's constantly at 90 decibels. And you'll notice that's not really all that loud.
It's like a vacuum cleaner sound, right?
Pretty much. Leaf blowers are over 90 decibels. Lawn mowers are over 90 decibels. Now, the big thing about that 90 decibel number is that that's an 8-hour time weighted average. So if you're out there using your leaf blower for a few minutes, that's one thing. But if you're out there and your job is to use a leaf blower all day, that's an entirely different thing. So we do have, you should be wearing hearing protection if you're mowing the lawn. You should be wearing hearing protection if you're mowing the lawn. And you can get hearing protection all over the place, and you should be doing it. Now, the rule of thumb is, how do I know when something's 90 decibels? You all can actually do it. First of all, if you have a smartphone, you can get a decibel meter on your phone. It's really pretty cool. You can also get a frequency detector on your phone. It's pretty cool. So you can actually get it. In fact, I did the experiment. I live across the street from a compressor station, and we've talked about how things fall off in terms of intensity. They go as 1/R². So I actually did the experiment, measured the sound of the compressor station at my mailbox, and then measured the sound of the compressor station at my house, which is a 1/4 mile away, and actually did the calculation. It's pretty cool. So you can do it. So you can use your phone to measure decibel levels. But if OSHA says if you have to raise your voice in order to be heard from normal conversation, you're probably close to a piece of equipment that is over 90 decibels. So how do you avoid that? You step away from it, and it's going to fall off as 1/R². So you will get that. So we have a whole lot of different ones. So this is the trumpet problem. This is the problem that we talked about here about dealing with your logarithms. So if I have a trumpet that has 75 decibels and we add 4 more at the same level, we're going to look at how that affects the change in sound. So I start out at 75 decibels. That's my initial one. I'm going to add the 4 more. So that's going to be 4 times the intensity inside the logarithm. That's where this is. All right? 4 times the intensity inside the logarithm. And you can break up your logs to do that. So it's 10 times log 4. And that's going to increase by 6 decibels. So even adding 4 trumpets, what it does is we go from 75 decibels to 81 decibels. And then you can review those logarithms in Appendix A11.
So which means if you have at work, if you have 4 equipment of 75 decibel each, the decibel will increase by
The 6.
6. It doesn't increase by adding
No.
all of them.
No. Doesn't increase by adding all of them. So we utilize that. So I'll give you guys a second, because we haven't probably used logarithms in a while, right? It's been a while since you've used logarithms. Been a while since you used logarithms. But that's, so and I know you guys have a homework problem that's got the logarithms in there. So you can calculate the intensity if you're given the decibel level. And you'll need to remember, so next Wednesday, you will be able to have a cheat sheet, okay, on your test. One of the things you probably want to write on the cheat sheet is that the threshold of hearing is 10 times 10 to the minus 12 watts per meter squared. It's one of those things that you'll probably want to have on there. And so if they give you the decibel level, you can go back and calculate it and just reverse it. But again, since you haven't used logarithms in a while, I suggest that you practice a couple of these, because it really does help. So sound waves are spherical. We've talked about that already. and we've got an average pressure per unit area. And so what's happening when that sound wave goes out, my area of a sphere, the surface area of a sphere is 4 pi r squared. And that's why we say that the intensity drops off as 1 over r squared. So if I start out with a big bang that I'm right up close to, how I hear it down the way is something that's a little different. Because the intensity is going, and you all know it, right? If we've had a thunderstorm and we get a clap of thunder and that lightning bolt is right next to the house, that shakes the house. But if we're a mile away, we just hear a rumble. Because the sound intensity is 1 over r squared. Same thing with earthquakes. Okay? Same thing with earthquakes. You guys remember the Shawnee earthquake, or the Pawnee earthquake a couple years ago? Happened around Memorial Day, or Labor Day, happened around Labor Day. Happened on a Saturday morning at about 8 o'clock. Well, that was kind of interesting because where I live now, which was my daughter's house at the time, and where I lived in Ponca, were on the straight line from the epicenter of that earthquake. We actually calculated it. It was pretty cool. And it calculated just how different the intensity was at my house versus the intensity was at her house. And as the crow flies, there was only a 5-mile difference between the two houses. But we were able, her house really, really shook. Things fell off the shelves. She had things fall off the shelves. She had a couple pictures fall off the walls. At my house, things sweaved and swerved, and you could see things swung, but we didn't have anything fall. So earthquakes fall off as 1 over r squared. Also, as we start going through the semester, we're going to look at electric fields. We're going to look, and we already looked at gravitational fields as well. Think of Newton's law of universal gravitation. It goes as 1 over r squared. We're going to see other fields go as 1 over r squared. When in doubt, things fall off as 1 over r squared. So that's a helpful thing for when you guys are taking your MCATs or whatever down the road. So we're going to lose that intensity of 1 over r squared. So we can compare the intensities at 2 different sources. This is exactly what I did with with the compressor station and my house. The thing where this falls off, all right? The thing where this falls off is I have to be just a little bit away from my source because I can't go as 1 over 0, right? I have to be a little ways away from my source. I can't go as 1 over 0 because that becomes infinite. So we can use that intensity to get us somewhere. So now we can talk about how we represent a sound wave as a spherical front. Because we're going to get into the Doppler effect. Okay, we're about to get into the Doppler effect. We're about to get into sonic waves. We're about to get into a bunch of this stuff. So sound's going to go out, and it's going to go out as a sphere. We can interpret it a couple of ways. One is we can look at it as that sphere is moving out, just like the ripple in a pond. The other way is we can use an arrow to describe the direction. So we can do both ways. But I want to look at sound, especially when we're looking at from the Doppler effect point of view, is if I have my source, and my source is just sitting there, and it lets out a peep, 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 a nice steady peep, I'm going to get a sound wave that's going to ripple out, followed by the next sound wave that's going to ripple out, followed by the next sound wave that's rippled out, and the spacing between the 2 sound waves is going to stay the same, provided that I'm peeping at a steady frequency. Now things are going to happen if I'm standing someplace, right? I'm the buoy in the lake, and I'm at a frequency sending out a water wave, that buoy is going to see the wave at the same time each time. Now, if I'm on a boat and I start peeping, that buoy is going to see things happen a little differently. But if I'm a person and I am on the watercraft and it's the buoy that's making the peeping sound, I'm going to perceive the waves hitting me differently. And that's what's going to happen with our Doppler effect. And we're going to see that here in a second. Now, the further away from it, it's like looking at our spot on the earth. We're sitting on the surface of the earth and we're looking in this room. And this room looks flat to us, looks like a plane to us, because the size of our sphere is great big. Same thing's going to happen with our sound. We can describe it as a planar wave as it's coming towards us. So we can describe a wavefront looking something like this. Now, I'm going to go back here and talk about this for a second, because we're about to hit, when we get in a couple weeks, we're going to be looking at electric fields. We're going to be looking at magnetic fields. And we're going to be looking at that plane in very much the same way, which is why I like to do sound as part of physics too, and waves as part of physics too, because we're going to be utilizing these same descriptors for waves and planes and rays as we just did here in sound. And with sound, we can kind of picture it in our head. Electric fields, not so much. But with sound, we can picture it in our head. So we can look at that, and the wavelength is the distance between the surfaces that we've got. So we can look at those pieces. So the Doppler effect is when we don't have a stationary source, or when we don't have a stationary observer, or when we don't have both. Okay? I can be moving towards something that is giving off a sound. Think about when the police car is heading towards you and you're heading towards the police car, like you're passing them on US 60 or you're passing them on 412. Both the observer and the source are both moving at the same time. And you're going to hear the Doppler effect a little differently because of that. Most of the time we describe the Doppler effect as you're standing on the street corner and the siren is coming to you. Right? That's most of the time when we talk about it. So the Doppler effect, so a couple things we want to do. We want to understand that either the source or the observer is moving, or both of them. And when the source and the observer are moving towards each other, we're going to hear at a higher frequency. And we're moving away from each other, we're going to hear at a lower frequency. And we're about to show you why. I got pictures. That's to show you why. Now, the Doppler effect only has to have a wave. Now, we hear it with sound, but we also call it a shift with stars. We can tell if a star is moving closer to us or further away from us by whether or not we're seeing a red shift or a blue shift. Same thing. Absolutely the same thing. Now you all know, can everybody spot the constellation Orion in the night sky?
Is that the Big Dipper?
No, Orion's the 3 stars across the middle, has some stars on one side that looks like a sword, and it has 4 big stars on each side. So it's Orion the Hunter. The Dippers are towards the north. Orion right now, if I'm outside, it's kind of on an equator part, if I'm looking at the night sky.
It comes off the Dipper though?
No, it's not on the Dipper at all.
No.
The Dippers are towards the north. Orion is going to be, the story of Orion, it's the hunter he's got a dog out there. There's a dog out there, Sirius is out there. And you've got the Pleiades, which are 8 stars together because he's supposedly chasing these 8 women. We only see 7 because the 8th star is really, really dim. That's the story. But anyway, go look it up, because Orion is really pretty spectacular right now. The star Betelgeuse, which is the star on the same side as where the sword is used to be, like in June, was the 8th brightest star in the night sky. It's usually between 8 and 10, depending on where it is in its cycle. Right now, it's like the 21st brightest star in the sky. And it's happened over a period of about 3 months. Betelgeuse is a red giant, and it's in its death throes. It's 640 light years away. 640 light years away. And astronomers are really watching it pretty significantly because it has gone through these dimming patterns before, but this is the dimmest that it's ever been recorded.
Go.
The odds are that it will go supernova anytime between now and 1,000 years from now, which in astronomical terms is like any day now, you know.
Right.
Any day now it can go.
And if it went supernova, would it take 600 years for us to see it?
Yeah, which means if it goes supernova, it happened in the Middle Ages.
Huh.
Because it will have taken 640 years for the light to get to us. So that's why, right now, if you read the articles around Christmas time, there was a bunch of articles, is Betelgeuse going to go supernova? If Betelgeuse does go supernova in our lifetimes, it's going to be a pretty spectacular event.
Like us, as in us seeing it.
As us seeing it.
Okay.
If for us to see it, if it has happened so that we see it in our lifetime, it will be bright enough for us to see it during the daytime.
Ooh.
Oh, that'll be cool.
That might be worth like flying to the opposite side of the world just to see it at night.
Well, no, you'll see it because you'll see Betelgeuse all the time. So and they say it will last for about they think it will last 3 to 5 days.
Like the constant light there.
Yeah. Mm-hmm.
Like bright enough to see in the day for 3 to 5 days.
Yeah. Uh-huh. Yeah, it's so Betelgeuse is worth going out and looking at. Betelgeuse is worth going out and looking at it because even I am able to detect color changes in it. So it looks a lot redder now than it used to. Mm-hmm. If you've been following it for a while, you're going. So if you go out and watch Betelgeuse is doing some really cool things. So it's really spectacular to watch. Betelgeuse, its size right now, just to give you a comparison of the size, because it's a red giant. If we were to put Betelgeuse and where our sun is, Betelgeuse would swallow everything up to Jupiter. So it's a big star. It is a big star.
Big stars are too.
Yeah, and it would take up all that space in our solar system. So Betelgeuse people are watching it. They're saying they're not sure if this is just a normal cycle for this star or not, but there's a likelihood that it could supernova, and the question is when, but it's likelihood within the next 1,000 years we would see the light from Betelgeuse.
And if it's that bright in the day, how bright would it be at night?
It's going to be really bright.
Like, would it be like us, like our sun at night, or would it just be like a bright?
That I'm not sure. They're estimating it. There's about several different articles. Go look it up. They'll actually show it. There's some good YouTubes on it about it. There's some really cool things that makes it kind of interesting. But Betelgeuse is a real interesting one. The last time a supernova was bright enough to see in the daytime is called Kepler's star, and it happened in 1604.
Oh.
Okay. So we look at the Doppler effect in there. There's a couple of things about the assumption. The Doppler effect is that the air is stationary and the speed measurements are made relative to stationary medium. So we're looking at the Doppler effect. So this time the source is stationary and the observer is moving. And the observer is moving, so if it hits a wavefront, because they're moving towards it, it's going to hit the second wavefront sooner than that wavelength. It's going to hit the next wavefront sooner. And so we're going to get a perception of increased frequency. And if I'm moving away, it's taking that wavefront longer for me to get to me. So we can look at animations associated with it. Example of the Doppler effect, so we can look at it, so we can play. So there is my source that's moving, and you can see what's happening to the wavefront.
Wow.
Okay, you can see what's happening to the wavefront.
Is this like the same thing with the blue or red shift?
Yeah, and the idea is the frequency of red light
Yeah.
is longer than the frequency of blue light. So that's why you have a blue or red shift.
But the blue is actually hotter, or? is
Blue-
this- Oh, this is.
This is, no, the blue shift for light, remember your frequencies of your wavelengths for light. It's blue shifts, the frequencies for blue is the shorter frequencies, red have longer frequencies.
Oh,
Yeah, it's the exact same thing, we're dealing with frequency. So that's the Doppler effect with the moving source, this is the Doppler effect with the moving observer. And I actually did the recording. And there's the Doppler effect in water waves. So if you're on the boat,
yeah, I saw that video.
no.
I couldn't really hear anything.
Well, that one doesn't have this one's just looking at the waves. Okay, so you can see it there. And so you can play with these. This is the example of the Doppler effect, just a straight Doppler effect. And it doesn't matter, we typically do the Doppler effect with a siren or a horn honk, right? I've heard the Doppler effect with geese. I've heard the Doppler effect with babies crying. Heard the Doppler effect with a variety of different things. You can create the Doppler effect with an open tube. So you can get the Doppler effect a number of different ways. So I used to have, but I was getting too many of the same things. Used to have you guys go out and record your own example of the Doppler effect. But it's been entertaining. Totally entertaining. So we get the Doppler effect that works out there. So if this is one of the things, and when you're doing your homework, this is where snags are going to come in. The homework is if I'm dealing with my frequencies, keeping track of their speeds, keeping track of what the speed is and how you put it into the equation. All right? The V sub 0 in this one case is the speed of the observer. Okay?
So the general equation for it.
There is a general equation. We'll see it in a second. It's easier sometimes you want to keep it tracked there and then look at it, and we've already seen how that's going to be there from the source. If the source is moving towards the observer, we get the source in motion, and now we have S for source. And then you get the general equation that has both of them. And it's keeping track of which one is the observer, which one is the source, is really the one that's going to cause you your grief on your homework.
Which one is moving away and which one is
Right, and then keeping track of your positive and negative signs. It's not that this equation is hard, it's just, okay, which value do I have to plug in where? So you got to be really careful when you're working with it. But that's the general equation that's used for both cases. And in one case, it's like, okay, if my source isn't moving, I can set the source to 0. If my observer isn't moving, I can set my observer to 0. And so that's why you've got to keep track of it. Now I'm going to ask a question. Do you hear the Doppler effect when the train is blowing its horn as it's crossing the intersection if you're on the train?
No.
Nope, because you're traveling at the same speed as the train is. Just like you don't hear the Doppler. If you're riding in the police car with the siren, you're not going to hear the siren. You'll hear the siren, but you're not going to hear the Doppler effect associated with it. Because you're traveling at the same speed as the source. Now, let's go back to look at that for a second, because I want to show you that for a second. Skip it. I want to escape. I want to go back here, and I want to do this with the moving observer. So we're going to go back. Okay. Look at what's happening. Now, this is a slow-moving source. Look what's happening to the waves in front of that source.
Is it a uniform distance?
Well, this one's moving at a uniform speed, so that one's going to be a uniform distance. But I want you to look at what's happening in the waves in front.
The waves are getting smaller in front.
Right, the waves are getting smaller in front. Now, let's think about this for a second. We said that if this is sound, what's the density doing?
Increasing?
We're increasing the density at that point. So we're increasing the density of where we're getting to at that point. So as I get further, as I'm moving faster and faster, those spaces are going to get smaller and smaller, right? That wavelength's going to get smaller and smaller. Now, if I'm approaching the speed of sound, what's about to happen?
You're catching up with your own wavelength?
I'm catching up with my own wavelengths. Hence the question that everybody had was, what's going to happen if I have an airplane that's going to catch up to its own waves? It's what people weren't 100% sure of. What's going to happen if somebody catches up to their own waves?
Is it gonna drop off?
No, doesn't drop off.
Well, I mean,
It
it's
just
sonic
stalls.
boom.
You're gonna get a sonic boom.
Isn't it because like, there's gonna be a force over there.
Speed of sound simulation. I just had a guy. They were measuring the speed of sound using an explosion. And I want to see if I have it in my. Let's drop on turntable, bowling balls. I did it last semester. Hang on for a second. Let me see if I can find it. Because we're getting close to the end of class anyway. So.
So is it gonna like inversely, like increase and then bounce back?
Well, that was the question. That was the question. It doesn't. We just go through the speed of sound and we have cool effects, but we get a sonic boom. I'll have to find it. There's one that they actually do an explosion and measure the speed, and you can actually see the sound wave and the density of the sound wave as we get there.
Does it push, it actually moves the other, the target or whatever?
Yeah, well, it breaks water balloons, but you can see the density of the air change as it's coming across. That's why I want it. So I've skip it. So what's happening is we build up a shock wave. That's what's going to happen, and that's why I wanted to show the video, because you can actually see the shock wave, and I'll see if I can find it. Where they actually they are disposing of some dynamite and have created the shock wave, and they've set up water balloons to actually measure the speed of the shock wave, so that that's how they actually do it. It's a really cool little video.
So is breaking the sound barrier what creates the shockwave, or?
Well, you when you break through it, that's when you're going to get the shock wave.
Okay.
Yeah, you're going to get the shock wave, and that's
Bust the balloons?
yeah, it'll bust the balloons. It'll break the balloons. Well, I have a great story. My grandfather worked for Idaho Power, And he was an engineer for Idaho Power, and he worked to help build every dam on the Snake River, from Bridger to outside in Oregon. And one of his jobs on one of the dams was to decommission the leftover TNT. Those of you who have been in my office will see that I actually have an Atlas dynamite box in my office. It's from my grandfather. My grandfather kept dynamite boxes and built shelves in his garage out of dynamite boxes. So it legitimately is a dynamite box. And his job was to get rid of the dynamite. And when they were building these dams, they'd build these little shanty towns, kind of shack houses, because we're back in the 30s, right? We're back in the 30s and 40s when they're building these things. And they have just built this dam, and he's the last guy out, and they're getting ready to do it. They don't think about it. The dynamite was in front of the dam, and they ended up creating a shockwave that ricocheted off the dam and plastered every one of those little shack houses. All laid them out all flat. Because the shockwaves will do stuff. If you've ever watched a building demolition, you see the shockwave. You totally see the shockwave. The shockwave comes through, it's there. You totally see it. And we get it, and that's what's happening is the source is getting to that point. So when we break the speed of sound, if the water conditions in the atmosphere are just right, you can actually see the cone. You can totally see the cone. The shockwave cone, and it's a vapor fog. But we didn't know until Chuck Yeager did it. We didn't know exactly what was going to go on. All right, we didn't know. So we get those water vapors. I'm going to stop there because we got 2 minutes left, and before we get into the characteristics of sound. But cool stuff. Sounds cool. Sounds totally cool.